Yep. So we have seen that from the approximation method that what we'll do, how to solve the concentration changes for weak acid or weak base, right? And what we can do if there is no clue at all of how much percentage of the acid or base is being dissolved or dissociated. So in that case, what should we do? If it is given that the pH is this much, we already know that what is the concentration of hydrogen ion there. If there is no information of how much is the pH is there, I mean, is being generated. So it is a blind guess. In that blind guess is just consider X amount has been dissociated from there and X amount has been produced, right? So this is another interesting thing that one X is being dissociated and one plus X and another 2X is being generated. So this is one thing. But the logic is if 1 mole is broken from here, 1 mole of hydrogen, 1 mole of nitrogen, nitrate ion is being produced. So that is why we are considering X. Everyone is all this number of molar X. So from there, we can produce the acid dissociation constant equation and put the value notation there and find what's the values there. Okay. Approximation method applying if it is less than 5 is good, if it is more than 5, no, it is not good, so we have to do it. The quadratic equation, from there, from quadratic equation, we will get two different type of roots. One is very much possible, another is impossible. So it is a negative one, which one cannot be possible for, concentration cannot be negative, right? Only sometimes you will see that this figure is very big, like 400, 4,000, which is impossible. One is quite simple or reliable or possible, another is impossible. So we do not take the impossible one. And that is how we will get the pH of the solution. Okay, this pH of ammonia, 4 mole ammonia solution. Ammonia is a weak base that we know, and again, this is as well, it will not be dissociated completely. It will not be, where my pen goes. Okay, it will not be dissociated completely from, so just consider X amount has been dissociated and plus X amount ammonia and hydroxide. Yeah, this is the same question actually. Just now we are discussing. It is been degenerated, but unlike the quiz question was saying that how much possible to produce, but actually it will not be produced because it is, a little bit of it is being partially has been produced or generated. So at equilibrium, we see that not fully, just a partial of it has been dissociated from the ammonia, and then we consider the base dissociation constant. So please take note of Ka and Kb. Ka is for acid, Kb is for base dissociation constant. So from there, we will again go for the approximation method, and we see that it is less than 5%, so it is okay to consider. The approximation is valid, and we can proceed further from there. Oh yeah, I think we did this much, right? And you're supposed to work on this from home, and I'm guessing that you already have done it from there at home. So which one will be the lowest acid, the lowest pH? From there we see that Ka value is here, so the higher the Ka, the stronger the acid, and the stronger the acid, the lower the pH in the solution. for the question, other question is saying that if the concentration of the acid identified in A1 is 0.015 molar, find the pH of this solution. If you are using approximation method, please test the validity. So A12, that is A1, question number A12, from among these three acids, if there is one acid which is having the 0.015 molar, and find the we have to find the pH from doing the ICE table. We know the initial concentration now, and all of the acids are weak acids, so we will consider the approximation method probably at the end, but we do not know the pH, so we have to take blindly X amount has been how much at equilibrium, how much will be left over. So just like the previous example, we will proceed and find the pH of the solution. So this is relative strength of conjugate acid and base pair. So this is, I think we also have discussed about it, I forgot, but this is a strong acid. The higher the strength of the acid, the stronger or higher the Ka of that acid. And here, interesting thing, we see that perchloric acid, right? The perchlorate ion, it is the weakest base. Hydrogen iodide, iodine is the weakest conjugate base. So stronger the acid, the conjugate base from that acid is the weakest. All right. So Ka and Kb of conjugate acid and base pair, we see that there will be conjugate acid and base, of course. So from that acid dissociation constant we can find, right? So it will be acid dissociation constant is hydrogen ion concentration times this A, that means the conjugate base that is being produced from here, and divided by the main acid HA, undissociated acid. This is the acid dissociation constant. But when this A is being hydrolyzed again, in any case, let's say it is hydrolyzed again in presence of water. So this is a base now because it is taking the hydrogen from the acid of water. So this is a base now, and therefore it should have a Kb. I don't need to write, I already have it. So there should be a Kb, and the expression of Kb in the similar way. Only the water will be not considered because water concentration is a small amount of water is needed. So its concentration almost constant. So these two, another important, interesting thing is if we sum these two up, right? If we sum these two up, we will see that we can cancel out the ions from the both sides. If we cancel out the ions from the both sides and the water is there at the end, water will be left here as it is. And that is why the Ka and Kb concentration, multiplication of the concentration should be equal to the Kw. This is another interesting thing. So we are coming back to water dissociation constant. From acid and base dissociation constant, we can come to the water dissociation constant again. To find Ka, or conjugate acid and base and weak acid, we just use these. Kw is always constant. At 25 degrees, Kw is, we know, right? It is constant. But if the Kb or Ka is given, right, so that we can find the other one from this type of equation. is quite easy. If we Kw is constant, that is water dissociation constant, but if we know the Ka or Kb, we can always know the other one because Ka and Kb. And this is important for you, please remember, because in the test probably you will have to do this. You will not be, I will not tell you that Ka is given, so please find out the Kb and then use that Kb here. You have to understand that how you will do it, how you will find the Kb to use it in the problem, to solve the problem. Okay, so Kw at 25 degrees is -14th, 10 power -14th, and it is constant at 25 degrees. Of course, with the temperature, it will change. Consider the following as two acids and their ionization constant, that is formic acid and hydrocyanic acid. And from these two Ka value of the two acids, we see that it is one is -4th, one is -10th. So which one is more stronger acid, do you think? Which one is more stronger acid? Which one is more stronger acid in this case, do you think? Of course, this one, right? Because this -4th is, how do you say, bigger than -10th, right? So -4 is better or stronger than -10. Give the formula of their conjugate base and comment which conjugate base is stronger. So as we know, the weaker the acid, the stronger the conjugate base, or the stronger the acid, the weaker the conjugate base. So for this case, we see that in this case, this is the weakest acid among these two. So its conjugate base will be stronger than that, than carboxylic group. And from here, it is also to some extent, it is it's evident that Ka for hydrocyanic acid is given, right? And formic acid is -4th. So formic acid, the Kb is -11th, but for hydrocyanic acid is -5th. So -5th is much stronger than -11th. Although it's very weak, but still among them is stronger. Okay, so this is ionization constant of some weak acid and bases as well. So how much it can ionize of this acid or base can help to ionize. This is the ionization constant. It can be found that the Ka and Kb for other some acids and bases. And most of the acid and base here, caffeine, that all everyday morning we take it, right? And for this methylamine, ethylamine, urea, we have this in our blood, urine to some extent. Aniline, we use it for our household sometimes. So these are very common acid and bases that we need. Sometimes we are using it. Yeah. Okay, so Lewis acids and bases. We already have learned about Arrhenius acid and base. Arrhenius acid and base. Can anybody tell me what is the definition of Arrhenius acid and base? What is Arrhenius acid and what is Arrhenius base? How do we define Arrhenius acid and base? Any idea? What is the definition of Bronsted-Lowry acid? No one? Where's the Bronsted, Lowry acid and base? Bronsted, Lowry. Bronsted, Lowry says that only based on the hydrogen ion, right? If we have hydrogen ion given, that is the acid. If somebody is taking that hydrogen ion, is the base. But for for Arrhenius, if any species is giving hydrogen ion, is the acid as well, but her base is whoever is giving hydroxyl ion. So Arrhenius, the definition based on both of them donating by different type of atoms, but donation. Bronsted Lowry is based on whether it is giving or taking the similar or same thing. But for Lewis structure, what is Lewis structure? For the Lewis structure, we see that a substance that can be donated a pair of electrons, and a substance that can accept a pair of electron. Now again, why it's starting? So for Lewis acid, it can donate a pair of electron, and for Lewis base, it will accept a pair of electron as well. So for this boron trifluoride and ammonia, even though boron does not have a pair or extra electron, but it is using, when they are together, and there are a Lewis structure for this compound as well, yeah. Interesting Lewis structure for this type of compound as well. So when they are forming, coming together, they are working as an acid and base. So boron, it can form one bond by just taking 2 electrons, and ammonia has one pair of electrons unused, just located on nitrogen, and it is not being used for bonding. So it can help to form the bonding and make a bonding there. So this is how they are using, they are behaving like acid and base, but not through other definition, only through Lewis definition, that acid and base. And carbon dioxide and water, when carbon dioxide is mixed in water, just like your soft drinks, there are carbon dioxide in the water has been dissolved. So they are also working in that exchange to some extent. They behave like acid and base, Lewis acid and base, by giving or donating or accepting this electron. What is the main difference? Can anybody tell you? You can consider this a semantic question. What is the main difference of Lewis acid and base and like Bronsted Lowry acid and base? What is the difference that you can see here? You'll see most of the time Lewis acid and base. Yeah, I have already made half of the answer. The rest half. Can anybody guess what is the difference? Yeah, Bronsted Lowry related to proton, that means hydrogen ion, but Lewis is based on electron. That is very good observation. And another thing, if you see that Lewis structure, that when they are having that exchange of electrons, acid and base relation, they are being together. They are being held together. Can you tell me why? Let me make it clearer. When there is a Bronsted and Lowry acid-base reaction, the proton is being donated, so they are making that H2O and ammonia, so ammonium hydroxide and hydrogen, something like that, like for Lewis acid and base, Bronsted-Lowry. But for Lewis acid and base, they are giving and taking, but they are staying together. They are not being dissociated or making different thing because of the exchange of electron. They exchange the electron for making an octet or anything like that for stable. So if they are exchanging electron, they cannot just give and leave away. They have to stay together for the donation, for the sake of this donation. If they break away, then they are taking the electron with them. So that is not there is no bonding at all anymore. And if there is no bonding, there is no exchange, and then they will not behave as acid and base again. So this is one difference. Acid-base properties of salt. So when acid and base are being reacting together, the salt and water will be produced, right? Some salts are ionic and ionize completely in water. So any type of salt, doesn't matter what the salt is, weak acid or weak base, or strong acid and strong base, or other mixed match type of acid and base reaction producing the salt and water, there will be any salt, right, which is very much completely ionized in the water. And then after that, it will further go hydrolyze with water and react with water. All right. So now you see that sodium chloride, potassium iodide, potassium nitrate, rubidium, all these is from group 1A, sodium, potassium, rubidium, cesium. So group A and 1 and 2, they are very much strong ions. They produce, and they produce the strong as base. Actually, they produce a strong base. So when they react with strong acid, they will produce this type of salts, right? And this type of salts, they will have the pH of around 7. If the cation from strong base and anion from weak acid, sorry. So cation from strong base, sodium will be cation, potassium will be cation. So they are coming from strong base, sodium hydroxide, potassium hydroxide. So they are very strong base. But acetic acid, the rest of the thing, CH3COO, this is coming from acetic acid or ethanoic acid, and they are not strong, they are weak acid. So this salt is being prepared or being produced from strong acid, strong base and weak acid. Since it is coming from strong base, so their anion is much more stronger, and that is why they will go for further hydrolysis and create a solution that is higher in pH, that means basic in nature. And the opposite is true for acidic, right? For the acidic solution, for salt that is coming from strong acid. Like ammonium chloride, ammonium nitrate, this is coming from sodium hydroxide, ammonium hydroxide and HCl. So ammonium hydroxide is being replaced by chloride, and it produces ammonium chloride, and it is not a strong base at all, because it is coming from weak base and strong acid. So this is a salt which will be less pH, that is less than 7 pH it will have. All right. This is easier to remember. If it is strong acid and strong base, it is always neutral. Sodium chloride is neutral. If it is strong acid and weak base, it is the pH will be less than 7. That means pH will be towards the acidic side. And if it is strong base and weak acid, it will go to the higher pH. That means the solution will be quite basic. But the problem is when there is weak acid and weak base. Okay, weak acid and weak base. When this is a weak acid and weak base, there is the problem. Both of them, positive and negative, both of them are weak, and weak coming from weak acid and weak base. And then pH will be less than 7 if the Kb is less than Ka. Kb means the base dissociation constant of that acid, of that salt, of the base that salt came from is less than the acidic ion came from that acid, then it will be less than 7. And if Kb is higher than Ka, it will be more than 7. So this is the only thing that will be a bit confusing. Not confusing because we can remember that if it is a similar weak acid and weak base, it is coming from, right? If the weak acid and weak base, then the acid and base that it came from, their Ka and Kb we have to consider. That means their the salt's mother and father, their Ka and Kb need to be analyzed. If the Ka is stronger than Kb, so it will be more acidic. If the Kb is more than Ka, so it will be towards the basic nature of the solution. So this type of generalization, actually this is quite much helpful for understanding the hydrolysis of the salt and which side the salt solution is going to be. And another example or another criteria is small but highly charged cation and ion form strong acid. So aluminium is strong because it cannot even fill up octet, right? It's small, but it has a highly charged. That means 3 positive charge is carrying the aluminium. Or iron is considerably small, but it also producing 3 positive charge on it. So they will form hydrated cation which is less than 7. That means it will be in acidic medium. The salt solution will be in acidic medium. It will have less than 7 pH. So neutral salt, is strong acid and strong base. It is coming from, I already have discussed it. I have talked about it. And the pH of the solution will always be around 7, not exactly 7, but yeah, it's very close to 7. Basic salt is the weak acid and strong base it is coming from. So the salt will have the hydrolysis of the salt will have more than 7, and it will become more than, pH will be more than 7, and extra hydroxide ion will be produced from hydrolysis of the reaction. So the CH3COOH is coming from the weak acid, right? And sodium. So here it is going to react with this and produce an acid as well. Again, the parent acid, it is producing the parent acid, right? But this hydroxyl ion is being produced again. So if we are going to go to the detail of the dissociation of acid and base, student, what they do is they are very much convinced that, okay, this is an acid, so it will be in acidic medium, but they forget that hydroxyl ion is much more stronger than this weak acid. This is the weak acid they are coming from, and they are producing it again, but this is a weak acid. But hydroxyl ion is much more stronger base from there, and that is why the pH will go up. Acidic salt, just the opposite way it will become, and strong acid as well. So it will be the acidic salt because of that, because of this hydrogen ion. Too much hydrogen ion is being produced from dissociation of this type of um, salts. What about the salt from weak acid and weak base? This is interesting, and we have already discussed about it. So Ka, if Ka is more than Kb, so acid salt will be acidic. If otherwise, it is basic, and if not, then it is neutral. Now we go to another example, that calculate the pH of 0.15 molar solution of sodium acetate. What is the percent hydrolysis of that salt? Calculate the pH of 0.15 molar sodium acetate. So sodium acetate is a strong or weak salt. Can we ask this type of question? That sodium acetate, is it strong or base, weak salt? Strong salt or weak salt? Can we ask this type of question? Is it valid question, do you think? Is it a valid question? No, it's not a valid question, because salts are always strong. Salt will be dissolved completely, doesn't matter from where it comes. And then it is not salt's problem of what type of solution they make. Their main duty is to dissociate fully salt, because they are electrolyte, right? So in this case, what percent of hydrolysis is going to happen for this type of salt when they are dissolved in the water? So 0.15 molar, 0.15 molar of salt, sodium acetate, has been dissolved in the water, and then we see we have to it will be completely dissociated in water. So all 1.15 molar of the salt will be dissociated and produce the same amount of sodium and acetate ion. Okay, same amount of sodium and acetate ion will be produced by sodium acetate. I mean, because of the salt, so 100% it will be dissolved. And interesting thing is, exact same amount of sodium and acetate are being produced. So among these, which one will be reacting? Sodium is coming, it originally came from a strong base, so it is much more inert, but so acetic acid, it will react. So this acetate ion, sorry, not acetate ion, is reacting to in presence of water, with water, and it's producing acetic acid and hydroxide ion, right? And hydroxyl ion. So if we consider that X amount of the equilibrium concentration of acetic acid and hydroxyl ion was produced at some point, we do not know how many percentage of this will be hydrolyzed. We know that 100% of the salt has been dissociated, so we have considered 100%, right? All 100, I mean, there is no salt left. There is no salt left, all produced to sodium and acetate. But after the acetate ion being dissociated, and it produces, acetate ion has been hydrolyzed, they are producing acetic acid and hydroxyl ion, right? And this hydroxyl ion is the question later on, that since hydroxyl ion is being produced, how much basic solution will it make? Right. So acetate ion has been produced and hydroxyl ion and acetate ion. So since it is also came from weak acid, right, the 100% is not going to be changed. A little bit of it will be dissociated or hydrolyzed. Okay, yeah, good. I forgot the word. A little bit of it will be hydrolyzed. And if it is hydrolyzed, that means water will be dissociated based on it. So that same amount of hydroxyl ion will be produced from there. Okay, so let's say we do not know how much, so blindly we just consider X amount. Since X amount of acetic acid mole on hydroxide ion will be produced the same way. And our main concern is this hydroxyl ion. If we know this hydroxyl ion, we can find the pH of the solution as well later on. So acetate ion is, this is the continuation of the previous example, yeah? So students sometimes may come in, they are just lost during this type of problem. They just do half and then they quit. They will not get mark, okay, if you do that way. So this is a continuation. Acetate ion was produced, water, and then this acetate ion is being dissociated or is being hydrolyzed in presence of water and producing acetic acid and what? Hydroxyl ion. Okay. But this acetate ion, since it came from weak acid, it will go further into the hydrolysis. And let's say that X amount of it, out of this 1.15 has been hydrolyzed, produces X amount of hydroxyl ion. So here, what it is behaving as, is it an acid or a base it is behaving as? Can anybody tell me what it is behaving as, acid or base? What do you think? Is it acid or it is a base? Yeah, it's better. So, hello, is it acid, do you think, or it's a base? What do you think? What it is behaving as, this acetate ion, this one? So this one, anyway, you will not talk. So this is hydrogen ion is being donated from water, right? Here, so it is taking one hydrogen ion from water. So according to Bronsted-Lowry, water is the acid and this acetate ion is a base here. So that is why it will be base dissociation constant Kb. We'll find the Kb, and we know that Kb for base dissociation constant for acetate ion is 5.6 times 10 power negative 10th. So from this way we can find what is the X. By approximation method, and if we know the approximation method, when we just consider it, approximation method, we find the pH of the solution, because we found the X means hydroxyl ion, and if we know the hydroxyl ion or the POH, we can find negative log of that value, and pH plus POH is altogether 14. Where's my cursor? Okay, pH plus POH is equal to 14, right? We have seen this before. pH plus POH pH plus POH is 14. altogether. So if we know POH, if we know the POH, we just deduct from here, we find the hydroxyl pH of the solution. So we find the pH of the solution is 8.96 from here. But the question is whether our approximation was valid. X is 9.2 times 10 negative 6, whether it is valid. So what should we do is we just divide by the initial concentration 0.15. 0.15 times 100%, and it is 0.0061. So it is even much less than 1. So it is quite okay, it's good. If it was not more, if it was more than 5%, we should do the quadratic equation from there. Now it is a first year question. It says that a student is given two solution, 0.1 molar ammonia solution and 0.1 molar ammonium chloride solution to study about acid-base equilibrium system. When the student conducted a simple test on the electrical conductivity of 0.1 molar ammonia solution, he found the solution to be weak electrolyte. He calls the ammonia dissociate partially in water according to the following equation. Explain in terms of its dissociation constant why 0.1 molar ammonia solution is weak electrolyte, right? So dissociation constant, it has a very weak and very small size or value so that it does not dissociate fully. Ammonia solution, it does not dissociate fully in water. Can we draw a Lewis structure of ammonia? NH3. NH3 is ammonia. So what is the main thing that we will be considering for drawing a Lewis structure? Total valence electron. Ammonia is 5 plus 3 hydrogen is 3 is 8 electron altogether, right? So if we draw this way in nitrogen, nitrogen, nitrogen and hydrogen, sorry, hydrogen, hydrogen, hydrogen. Actually, I shouldn't draw it that way. I should draw a little bit charismatic way. So, yeah, let's say nitrogen. Hey, okay, consider this is hydrogen. Consider this is hydrogen. And this is the hydrogen as well. So each of them has 2 electrons each, right? All the bondings are having 2 electrons each. Okay, 2 electrons each. So this is all together is 6 electrons. Then where is the another 2 electrons? Because I have to make sure that we have 8 electrons on this molecule. We will put another 2 electrons here on nitrogen, because nitrogen with the 3 hydrogen is not enough, or haven't formed the octet yet. So with these 2 electrons, it will form octet. So since now it is forming octet, nitrogen, they are stable now. They are quite stable. And they are stable and what do you call it? Okay, so they are stable. Hydrogen and 3 hydrogen, nitrogen and 3 hydrogen, they are stable. And they have all 8 electrons all around in nitrogen and 2 electrons in hydrogen. So they are quite stable, this ammonia. Okay, so this is a weak electrolyte. Ammonia solution is a weak electrolyte because it does not dissociate completely. That's why. Calculate the pH of 0.1 molar ammonia using approximation method. So if we have already the Kb is given, 0.1 molar of ammonia is being given here, and we know that is a weak acid. So by blindly we have to consider that X amount has been dissociated from here, from ammonia, right? So X amount has been dissociated in the change. So at the equilibrium 0.1 molar minus X, we will have minus X. So Kb will be 1.8 times 10 negative 15 and 0. X squared by 0.0. So from there we will find the approximation method, and of course we have to validate whether the approximation is valid or not. Acid base titration. This is the thing that we are going to do next week, lab, acid base titration, by using pH meter. This is the thing that we have already done it, right? So we slowly added acid and base in this through this burette to the conical flask, and we saw that the color is being changed, right? What are the difficulties this type of solution has? This type of technique has? Can anybody tell me what type of problem or what type of difficulties we have for this type of acid and base reaction or titration? Acid and base titration, what type of problem we have? Someone, I think Ainin showed me that color become too much pink, right? So in that case, you have added maybe 1 or 2 drops more, because of we are human, we are not machine, and that is why we cannot control all the thing at the very precise way, or precisely we can do our experiment. So that is why there is the problem of doing overshooting this type of solution and make it a mistake in the exam test. But if we had machine or instrument that it will tell us that, okay, stop here, this is the point we are reaching, so that it will be much easier. And this is the exact thing has been done by this pH meter. pH meter will tell us that we are done, you don't have to add any more. Okay, we are going there. So when we did this type of experiment, we reached to this type of color. I'm sure that many of you have taken more deeper than this color, but when this type of color or even faint than this color, your titration is done already, that you have already reached the end point. And the end point where the color is changing, which is, there is another point, equivalent point, right? There is another equivalent point which is not equal to the end point. We will be, I do have some slides later on, so I can show you later, or example for the equilibrium point. So this is the equivalence point, and you will not get the data for this equivalence point on your numerically from the experiment. It will have to be counted. This equivalence point has to be counted, because this you will not get a data from here. What you will get that sometimes you will see that acid and base pH curve. Oh, we have started the pH already, yeah. So this is the acid base titration by liquid or wet titration. That means we are adding 2 different things and then in a conical flask and then shaking and waiting for it to be pink. But if we do not have this way and we use the pH meter, so what we'll do is we put this. We put the pH probe into the solution and start adding the sodium, base or acid into that solution. So if we started with acid, and you are constantly adding base, so what will happen? The pH of the acid will increase, right? The pH of the acid will start to increase slowly, and then it will, to some point, it is going slowly because I am adding base in it, and then at some point there will be a sudden jump, and then again it start to reduce slowly and go, and then stay stable. No matter how much you add, it is stable there. So this part, the equivalence point is here. This is not the end point. End point is about this point, this here, that the reaction is being end. Reaction has been finished. That is the end point. But the equivalence point means this is the balance where I have exact amount of sodium hydroxyl and hydrogen ion in a broader sense, right? Hydroxyl and hydrogen ion in the broader sense. So this is the balanced way. This is the nicely balanced. So that is called the equivalence point, which is not to the end point. So if we do the weak acid and strong base pH curve using the pH meter, we will get this type of data. Weak acid, we started with the weak acid, we are adding strong base to this weak acid, so it started to increase, shoot up and then go and stop. It didn't go anymore. So this is the pH of the strong acid and strong base. But this is the half neutralization point, exactly half of this value, equivalence value, where it will be neutralized. This is the half of that, right? And then strong acid versus weak base. So now we are adding base. We are adding acid to a base. So we started from here. Since we in the conical flask we had base, so at the beginning the pH is very high for this, and then as we started to increase the concentration of acid, the pH continuously go down, right? pH, because every moment we are measuring the pH. So how does it look like? For this is a beaker. We will see it actually in the next class, but for the sake of understanding now in this class, this is a beaker and I am dipping the probe, the pH probe here. The solution is until this part, right? Solution is here, and this pH probe, of course, it is attached to the meter, pH meter, and from here we are adding the base. We are adding the base or acid to the solution, and it is giving us the value like 7.4, 7.8, something like that. It is giving us the value, pH value. So we will start to read the pH. We start from 11, and then we continuously go on until the pH reaches to like 2 or 3. So there at that point, the pH will be, we know that this is the end of it. An equivalence point. From there, later on, we will find the, put the data on Excel or graph paper, and we will take that, the middle point of the big jump, the leap. This is one here, right? It was coming down quite slowly, then jump from here to here. So between this here, we will find the middle point, and that middle point is the equivalence point for this. We will do it next week. And that is the half neutralization point. Half neutralization point is important for us to know the buffer solution as well. Okay. So one example is here that calculate the pH of equivalence point when 25 milliliter of 0.1 molar ammonia is titrated with 0.1 molar of HCl solution. Ammonia is being titrated HCl. Interesting thing is ammonium chloride is being produced, and this is a salt, so they can go further hydrolysis. That is one interesting thing and confusing thing. Don't be confused. You know that ammonium chloride is a salt and it is coming from a strong acid, weak base. So you can just produce a solution that will further go for hydrolysis. Okay, so ammonia and HCl, and it is being produced. Of course, they are being, since HCl is very strong acid, it will take up all of it. It will go for reaction and it will take all of it, and it will produce exact amount of ammonium chloride. And this ammonium chloride, so from here we find the number of moles or concentration, because 2 amount of sodium, ammonium and HCl has been added. Even let's say it's 50 milliliter, 50 milliliter, 20 milliliter, 20 milliliter. So all this amount of volume is being added up, so that there is a new concentration for ammonium chloride now. And this ammonium is further going for hydrolysis, just the way we have seen previously. So from there we find the pH of the solution is 5.2. What is the advantages of this? It is much accurate. We don't need the indicator. It's less chance of overshooting and all those things, right? So acid-base indicators. Next, please remind me in the next tutorial class to show you the acid-base indicator. I have a quite nice list of acid-base indicator and how good they look. So if you are there, please remind me of this acid-base indicator so I can show you. So acid-base indicators and common acid-base indicators: the thymol blue, bromophenol blue, methyl orange, phenolphthalein. Mostly we'll be using phenolphthalein is there. But the interesting thing is acid-base indicators, themselves are acid. They themselves are acid. So when their pH is changed, they change the color. That is what. So solution of red cabbage extract, we'll see later on in this. So as the pH is changing, it's a weak acid actually. pH indicator is acid, weak acid, and that ionizes within the known pH range, usually about 2 pH unit. And when they changes acid-base indicator, so it can donate hydrogen ion, but it is a very weak acid. It does not usually donate it. If there is a strong base to take this hydrogen and snatch the hydrogen from it, then only it will give the hydrogen. And in that case, it is donating. So they are producing this type of anion, which is responsible for this color. All right. So one thing. Another thing is, if it is there is a weak, a strong acid is there, so it can also take this acid and changes the color back. So that is why this is how the mechanism of how they are changing the color when we are added into the solution. And there is quite interesting data for different type of acids and bases that we have, indicators that will be used for acid-base indicator, and which one is giving the color in what range, pH range. And the pH range will be +-1. I will discuss this thing in the tutorial again. So this is the basically thing. 25 here, it will be the equivalence point. So 25 is 5.25 pH. It will be the here, and then around this point, it attained the equilibrium point. Yeah, so this is it for today. Do you have any question, anybody? I know that I kept you for so long. No, it is our normal time, right? It's our normal time. I know that you don't have a question, but I have one Menti question for you guys. Please go to the Menti question, mentimeter.com, and then use this code. This is not about acid and base, but this is about Lewis structure. Okay, and then vote it. The vote will be closed in 2 minutes. Okay, The vote will be closed in 2 minutes. So please go to there, to the which of the following has the most stability. There are 3 different compounds of nitrogen and oxygen. No, sorry, 1 compound of 3 different arrangement. So which one do you think is most stable? Go to menti.com, use that code 9518324 and then vote. You please vote, cast your vote to tell us which one is more stable. Okay, your time will be up in 10:42 now, 10:44. Okay, you have 1 minute to go now. Please do faster. I can see here there are 12 students, but only 1 or 2 are responding all the time. What is the problem? Twenty seconds. Ten seconds. Okay, so 1 student go for 1, B 4, and C also 1. Hide image again, show image, and show the correct answer. So yeah, good. Most of you have found the, choose the good one, the correct one. So B is the most stable component. And if you go to that the recorded session that I had on Canvas, you will find the explanation for why it is more stable. Okay, so tomorrow, that is why I will not have the class. Okay, and yeah, because I have completed it here today, this accident base, I'll not have the class tomorrow, but I will be online for some time. If you have any question or anybody is visiting me tomorrow, I will be online for some time. Okay, so all the best, take care. I'll see you next week.